All right. $24.13, day 14, which means this is the end of the 7th week. Yes, it is. All right. Now we're going to talk about the rules of differentiation, which is actually the shortcuts. Because if I would originally, so let's look at something 2x squared plus 3. In chapter 2, we learned how to find the derivative of that. How did we learn how to do it? In chapter 2, unfortunately, it was the epsilon delta. So then we talked about the Riemann sum, where we had the limit as x goes to 0 of the summation. Actually, let's make it n, because this was k equals 1 to n of our function times delta x. Adding up all these little slivers, that defined our function. Then we talked about the difference quotient. This got a little bit easier because the difference quotient finds the slope. But if we take the limit as h goes to 0, we just found the first derivative. The first derivative, in essence, we're getting to is the first derivative is the slope. So let's, for last time, let's do the difference quotient for this equation to find the slope. And then I'm going to show you the shortcut. So use this formula here. Find me the first derivative. Well, find me the first derivative at x equals 3. So to find the derivative, we need to take the limit as h goes to 0 of the difference quotient. We have f of x. We need f of x plus h. Right. X plus h squared plus 3 minus 2x squared plus 3. We have to figure out, we have to FOIL that first, or next, not first. We just did this first. So we have 2. The x plus h squared becomes x squared plus 2xh plus h squared plus 3 minus parentheses 2x squared plus 3. Remember, everything after the minus, everything here is supposed to cancel out. So let's distribute, get rid of the parentheses. We got 2x squared, 4xh, 2h squared plus 3. Now distribute the negative sign. Negative 2x squared minus 3. Cancel what we can. Factor out the h. Now,
0, 2 times 0, 0, 4 times 3 equals.
yeah, but once h goes to 0, then we just have 4x. So that's our first derivative. So our first derivative at 3 is 12. Pretty easy, but time consuming.
Right. Yeah, for sure.
But you read forward, so you know what's coming up.
Yeah. It's literally. I actually ran into it by accident. I was watching a video, and he just did it like that, and I was like, "What the heck?"
Yeah, but we now for this next section, we're gonna go through constants, multiples, exponents, rationals, products. We have to go through all those. And again, this will save us. We're gonna go through all of those by the time it takes us to do this.
Right.
Okay. So let's look at derivative of. First one, we're gonna deal with constant. The constant function. We don't really need calculus to show us this one. Because if we look at the graph of this equation, what does the graph of a constant function look like? Yeah. I always thought straight lines redundant. Yeah. Yeah, it crosses through A, and it's a horizontal line. The slope of this line is 0. The first derivative, remember, the first derivative is actually finding the slope of the line, slope of the curve at a point, since it's a line. So the derivative of a constant is 0. A linear equation. F of x equals x. The graph of this function is the diagonal line. And remember, the point slope formula, or slope intercept formula, y equals mx plus b. Whatever's in front of your x is your slope. So the slope of x, the first derivative of x is 1. And I'm going to show you why this is in the next one. And the quadratic equation, this will lead us into the power rule. The quadratic equation is x squared. So that's what x squared looks like. It's a parabola. The slope of a parabola changes depending on what point we're looking at. If we're looking at on the left side of the zero, we have a negative slope. If we look at the right-hand side, we have a positive slope. Whenever you have that, whenever one side's going down, one side's going up, eventually somewhere in the middle, you have to have a slope that doesn't exist. It's zero. It exists, but it's flat. The derivative of this one is 2x. This leads us what's called the power rule. Because the constant rule and the linear equation, we know those. If it's a constant, derivative 0. If it's a linear equation, the derivative is 1. But if our function is x to the power n, the derivative of this bring down the power and subtract 1. That's the rule. So if I gave you f of x equals x to the 15th, what's the first derivative? It's 14. Yeah.
So, for the quadratic equation, why do we say the derivative is 2x again?
No, yeah, we'll get there. I'm building it. I'm just giving you the basic structure right now, because that's why I'm using this one here.
Right.
Because remember, we use the constant rule, then the linear. Well, let's put them together. We're gonna start building them up and see what to do. When we do derivatives, we can take derivatives of each part separate, each term. We know we have 2 separate terms, so we could take them separately. What's the derivative of 3x? 3, because the derivative of x is what? 1. So if that goes to 1, then it's just 3. What's the derivative of 5? 0. There's a constant. So the derivative of a linear equation is simply the slope. Right, so again, we can take these piece by piece by piece. Again, and remember, notation-wise, all of these are the same. I mean, remember last time that we put a whole bunch of them up there, like 9 of them. So what's really happening here, what's really happening with this equation here is for me to find the derivative of the function with respect to x. That's whatever's on the bottom is what I'm taking with respect to. What I'm doing is I'm doing each of these separately. So the derivative of 3x is 3. And derivative of 5 is 0. Now, why is the derivative of 3x 3? Well, yeah, because 3 is a constant. We could take it outside the operation and then take the derivative of x, which is 1. So 3 times 1 is whatever the coefficient is. Okay.
Is the word the denominator is the same, right?
What's that?
Just can use if you derivatives, just both the denominators are the same.
Well, the denominator tells us what variable we're taking the derivative of.
Oh,
Because later on in this course, we're going to take derivative of x and y. So x, y, and z, if you want to have a 3-dimensional function.
wait, is that so it's d 3x over dx plus d.
Yeah, it's the derivative of 3x with respect to x, the derivative of 5 with respect to x. Because it's this function here.
Right. And then
Yeah, it's a constant, so it's 0. So, which is what you were asking. Let's say we had 4x to the 5th plus 3x to the 3rd minus 2x plus 7. Find the derivative of that one.
the 16 x to the power.
What's the derivative of x?
20x.
20x, because it becomes the constant is so the derivative of 5 x to the 5th is 5x to the 4th.
And then plus 9x squared
Right.
minus 2.
So it's going to be 20x to the 4th. And that's the derivative. Yes, and we talk about constants. We have constant multiples. We have power. And with this rule here, what I forgot to tell you about is it's a sum and difference rule. If you have a polynomial, you could take the derivative of each one separately and then combine them at the end.
Sum of 2 functions.
Is the sum of the derivatives. Right. The derivative of the sum is the sum of the derivatives, right? And
Just like with the limit space.
exactly. That's exactly what, yeah. All these rules now, if it applies to one, it has to apply. If it applies to limits, it has to apply to these.
Okay.
And then conversely, if it applies to these, we have to be able to put it into limits. Here I have an example sheet. Yay. I'm gonna wait for these. Let's do these 4. Find the derivative of this. Whoops, right. Find the derivative of these. B is
1/3, or negative 1/3. That's, yeah, there's no fraction, yeah.
I know you guys hate fractions.
Is it negative 1/3?
So what's the answer going to be? Yeah, because 2/3 minus 1 is 2/3 minus 3/3, which is negative 1/3, which becomes 2/3 cube root of x. How about C?
Can you change this to what?
No.
You can change it to 1/, to x to the power 1/2.
So square root of 2 is square root of 2 minus 1.
Mm-hmm. But square root of 2 is a number. It's just, it's a different symbol. Let's see this one. This is 1/x to the 4th. What's the derivative of this one? Remember, we have to use the only rule we know so far is the power rule. And the constant and the quotient. I mean, but
So 3 times 1/x to the power.
no.
Or 4 times 1/3.
No. Rewrite the scene first so you have a power. Because we haven't talked about it being on the bottom. How do we get it off the bottom? The negative exponent should be tells change location. So it's negative 4 x to the negative 5th, right? So the answer is negative 4/x to the 5th. So you have to, if you have a fraction, if x is on the bottom, you have to change the exponents. You have to put it on top and change the exponent from positive to negative. E so what's the derivative of x to the negative 4/3? Negative 4/3 x to the power negative 7/3, right? Again, it's the hardest part is when you move this down, subtract by 1. You have common denominator already. And well, actually, before we do, well, we'll do F. X to the power 2 plus pi in the radical. So how are you going to do this one?
Do we need to change this word?
Oh no, what do you think?
Say,
Do you know any rule about square roots? So the only thing the only thing we know is the power rule.
Plus pi times the square root of x to the power 2 plus pi minus 1.
Because this radical is to power 1/2. So, and then power to a power you multiply. So the derivative of this is 2 plus pi over 2, x to the power 2 plus pi over 2 minus 1.
So I actually.
You could do 2 over 2, which becomes 2 plus pi minus 2 over 2, which makes it pi over 2. So the answer is 2 plus pi over 2, x to the pi over 2. What about if you have a negative coefficient? Will that change anything? If you take a derivative of a term of an equation that has a negative coefficient,
Then you would, so you would just, keep the negative there and you would multiply it. by-
Exactly. Exactly, yeah, if you have a negative coefficient, the answer is negative, it's just whatever the derivative is. That's what this example was. It wasn't even an example, it was just a discussion about. If you take the derivative of 3x squared, it'd be 6 power x, or 6x to the power 1. But if it's negative, keep it negative. Now you will remember we did substitution. U is a function of x. So when we take the derivative of u, we just get du. So that's what we did here. We took the derivative of u, we got du.
If we're just doing substitute, and do substitute.
Pretty much same thing, yeah. So the derivative of u is du. That was pretty easy.
Negative d would have a negative.
Right, yes. Okay, we could do this one pretty quick in your heads. What's y prime?
3x squared plus 8 3 minus 5.
That's it. I mean, think of how long this would have taken us with the limit or the epsilon delta.
We
I
would be
mean,
sitting there forever.
Exactly. That's I would have been able to finish my chips. That's why I was excited about this section. It's a respite for us. Does the curve y equal x to the fourth minus 2x squared plus 2 have any horizontal line tangent lines? If so, where?
So we just you would have to find the derivative first.
Okay, so let's see this. If we find the derivative, what do we get?
4x cubed minus 4x. And we got equals
So where would the horizontal tangent line be? X equals 0? No. You were close though.
2.
No.
Almost.
But it is going to be, one of our answers is going to be 0. Yes, but that's not how what it's looking for. When it says horizontal line tangent line, what does that look like? It's like this, right? What's the slope of that line? Which is the first derivative. So we set our first derivative equal to 0 and solve for x. This is the where.
So why?
Yes, because what we're looking for when the horizontal line is 0, the slope is 0. Where is the slope 0? We set the equation. Well, y prime is 0 because y prime is the m. So we factor out a 4x out of both of those. Because this, remember, this tells us that we're going to have 3 intercepts at most, or 3 solutions in this case. This, fortunately for us, is a difference of 2 squares. X plus 1, x minus 1. So our tangent lines being 0 occur when any of these equals 0. At x equals 0, x equals -1, and x equals +1.
Factor.
Pretty much, yeah. Because once you take the first derivative, set it equal to 0, because remember the first derivative is slope, set slope equals 0, and you then all of our vertices occur here. Now, if it wants us to find points, we would take these and plug them back into the original equation. What's that? Well, it's like the quadratic. It's quadratic like, because we have, this is, whenever you look, you can use the quadratic formula for this one, because you notice when you do the quadratic formula, the negative b plus or minus whatever.
What we're really just, what we're doing is finding the roots of all of them.
Right. And a quadratic equation looks like this. So whenever you solve for it, you look at the middle term. That's what you're solving for. And if you take the middle term and square it, do you get this one? If that's yes, then you have a quadratic-like equation. This one's squared. If I square it, I get 4. So this one is quadratic-like. Because what I'm going to have here is x squared, x squared. If it's factorable. If not, then I can do something else. But what this question is looking for is basically it's asking for find any vertices or any vertex. Remember, vertex is either the highest or the lowest points where the slope is 0. So that's how you find your vertex. So they occur at x equals 0, x equals -1, and x equals 1. The location of those we have to work them out. So when x is 0, y is 2. There's our first vertex. Our second vertex is 1 minus 2 plus 2, so it's 1. 1 minus 2 is also, because the 2's cancel out. So these, if so, where? They occur at x equals 0 at here, but they are at. So it all depends on what the question wants on the computer. So you try, if it wants the x-intercepts, if it wants points, and give them. So.
Like if it wants an equation, but x equals.
Right. So yeah, again, it varies on how they phrase the question. Okay, another with respect to the power rule. Here I'm talking about the natural log. E to the x. So if your function is e to the power x, the derivative is the derivative of your exponent times e to the power x. So in this case, what's the derivative of x? The derivative of x is 1 times e to the x, which is e to the x. So the derivative of e to the x is e to the x. The derivative of e to the 5x five e to the 5x, right? So that's why e's are easy, because I can now expand the rule for you. E to the power u, where u is some function of x. The derivative is eu times the derivative of the exponent. And that's what we're doing here. E, leave this alone, take the derivative of the exponent. And that's all there is to it.
Basically, refining the derivative of the x.
Yeah, and just copy and paste it back down, right? Whatever this is, times derivative of that. It's that's why it was super. That's not even a bigger rest. Okay, how about this one? If we can read it, find the equation of the line that is tangent to the graph of y equals e to the power x and goes through the origin. So how would you go about solving this one? What is it asking?
Find the derivative.
No, it's part of it, but that's not what it's asking. It wants an equation. So it wants y equals mx plus b type thing. That is tangent to the graph of this at the origin. At the origin is 0, 0. In order to find an equation of the line, it's linear. You need to have two things, a point and a slope. To find the equation of a line, we need those two. This isn't calculus, it's algebra. And it's the algebra parts that are going to throw you for a loop. Because you're going to think, oh no, it can't be, it's just too easy. So we have a point. Our point is 0, 0, because that's the origin. Now we have to find the slope. What's the slope? How do we find the slope? First derivative, which is what? Of e to the x. Since we're at this point, we need to have the slope at that point. So x is 0. E to the 0, so it equals 1. So the slope is 1. So we have the x, we have the y, we have the M. All we're missing is the B. So 0 equals 1 times 0 plus B. That's 0. So B is equal to 0. So the equation of the line with slope 1 going through 0, 0 is y equals mx plus b. One x plus 0, y equals x. That's your equation of the line going through the that function at the origin. So far, so good. Now we gotta throw the wrench in there to learn how to do something mathematical. Well, so far, these have been pretty easy rules. Let's look at the product and quotient rules of derivatives. Let's look at the product first. Let's say that we have a function h of x. It's made up of a product of two other functions, f of x times g of x. What would be the derivative of our main function? A lot of people try to make you just memorize the formula, but they get confusing after a while. Here's the way I always do it. I have my f and g, whatever they are. And then right below those, I take the derivatives of them. The formula, when you're multiplying, it makes things bigger, right? So starting from the G, make that little fishy thingy. And since we're multiplying, we put a plus between them. And there's your formula. You start off with G, right? So we went from G of x times f prime of x plus, we go the other way, f of x times g prime of x. Because you're going down and then down. Ooh, I'm gonna try one here. We're gonna do this in two ways. And we should get the same answer. So what is our f of x? What functions are f of x? It's 3x squared. It's the first equation. And g of x
Oh,
is the second one. No, we haven't gotten there. We have first label f and g. Yeah, so the first one is f, the second one is g. What's the derivative of f? 6x. What's the derivative of g? 2. Because the derivative of 1 is 0. So we do since we're multiplying, we add them. So the derivative is going to be g of x times f prime of x plus f of x g prime of x. So it's 2x plus 1 times 6x plus 3x squared times 2. Get rid of parentheses. So 6x times 2x is 12x squared. 6 times 1 is 6 plus 6x. 2 times 3 is 6x squared. $18x squared plus 6x.
Okay, that's a really good choice there.
The
Okay.
fish.
Yeah,
Yeah, but because it makes it, you'll never have to memorize the formula.
that, and it's one of those things where it's like, it doesn't make it slower, really.
Actually, it speeds it up.
Yeah, memorizing. Because you're not sitting there, searching your memory.
Exactly, because the next formula with quotient, it looks like that, but a little bit different. But let's try it. Okay, let's see if this is our right answer. Let's first multiply these out first. So we have h of x, 3 times 2 is 6. X squared times x is x cubed plus 3x squared. Yeah, so the same thing. So now you know that if it's an easy equation, you can combine them first, or if it's two large polynomials, do them separately. Let's look at this example. Oh no, because we haven't done that one yet. Let's do quotient rule. So that's the product rule. That's the product rule. Because we use plus because multiplication makes things bigger. The quotient rule deals with fractions. So let's say we have a function h of x made up of two functions, a numerator and denominator. As long as g of x is not 0. The derivative of h of x is going to remain a fraction. We do this exact same thing we did for the product. We put the fishy in there. But Since we're dividing and dividing makes things smaller, we subtract. So it's going to be g of x times f prime of x minus f of x times g prime of x. And the bottom is g of x squared. So there's that formula.
What is the bottom of the squared?
I'm glad you asked. If we take this function and take the derivative of it, this would be x to the power -1. So the derivative using the power rule would be -1 x to the power -2, which would be -1 over x squared. So whenever you have an x on the bottom and you take a derivative, it always increases it by 1. Simply because of this. If I took the derivative of this one, I'd have a -2, and now I have a -3 on the bottom. So since it started off as g of x, that means it's g of x squared. I bet you're great at those infomercials at the fair. How did you get that? Can you get anything more?
Yeah.
What else can I do, Bob? Okay, let's say we have our function f of x, h of x made up of 3x squared plus 2 over 2x plus 1. Find h prime. First thing, what is f? 3x squared plus 2. G is 2x plus 1. F prime, G prime. Since it's a fraction, we subtract. G f prime, f g prime over g squared. So we have 2x plus 1 times 6x. 3x squared plus 2 times 2. All over 2x plus 1 squared. We have 12x squared, 6, minus 6x squared, minus 4.
Times 6x squared.
Yeah, 12 minus 6 is 6. And there's a derivative. Yeah, now you see why it's much easier now, because the formulas, if you put the wrong combination, it doesn't matter in the product. You could put f g prime plus, but it's very important here. If you put it the other way, you get a negative answer.
That's like a memory stick. That's like an external, like you memorize that little thing right there, and then you can put that on your paper. And whatever
Is it-
you're doing, that acts as a benchmark.
Exactly, yeah, and I can't tell you, when I first learned calculus in my class back here, half the people got the formula wrong because they juxtaposed it. I couldn't remember the formula. So once I started teaching my first semester of calculus, I was teaching it. I said, "Hey, this is exactly what it looks like." And I used a little fishy thingy, and it's stuck with me ever since.
Right.
Okay, so it's the fishy
And
thing.
it's nice because you start, you just have to remember, you start in the top right and you follow the line.
And yeah, if I asked you to draw the fish, how would you draw? You'd always draw the top right and into the bottom. Okay, so here we have the next three sheets. Grow a little bit more difficult. So go ahead and do these two. All right. We have y equals 1 over x times x squared plus e to the power x. There are 3 or 4 different ways you can do this. Which way did you choose?
I chose the quotient.
Okay. What did you choose?
I use the exponent.
The exponent one?
I use scale so that's the one. So then I thought that's why I'm confused.
Well, for the quotient rule, I just put the, you know, since there was already a 1 in the numerator there, is the x squared plus e to the power of x over x.
Okay, let's look at that. So f is the x squared plus e to the x. G is equal to x. F prime is 2
Plus e to the
e to the x, and g prime is 1.
x.
That was better than the portion.
I
So-
just always, if I can use some kind of a quotient rule, if there's something in the numerators in the 1, I always try to do that. That's kind of my personal strategy.
Actually, yeah, and it usually always works. And what's on the bottom? X squared.
2x squared plus e to the x, or plus x e to the x, minus x squared minus e to the x over x squared. And then I didn't know how to simplify.
Okay, 2x squared minus 1x squared is x squared.
Oh, yes. X squared. That's in simple form.
Yeah, there's not much we can go any further from there.
Right. Okay.
Let's see if there's another way. We could have converted this one,
Yeah, that's the one.
which would not have been wrong. You use the product rule. So add the exponents, so it's x to the power 1. You have x squared times x to the negative 1, same bases, add the exponents. That's where that came from. So now we just do the derivative of this. The derivative of x is 1. Now we gotta do the product rule anyway. But it's a lot shorter. This is e to the x. This one's gonna be negative 1. So it's gonna be negative x squared minus e to the x, x to the power -1 over e to the x squared. Okay, that's where it stopped being simple. Because now we have to get this thing has to be e to the power x squared over e to the power x squared. Common denominator. Minus e to the power x, x -2, e to the power x, x -1, all over e to the power x squared. No, that's plus, I'm sorry. So all of these have e to the power x in there, so we can factor that out. That cancels one of those. So this is going to be e to the power x over 1 plus 1 over x squared minus 1 over x. Interesting how this one's give us a different answer.
Well, if you, what if you multiply the numerator by 1 over e to the x?
Well, yeah, maybe, yeah,
Okay.
that's so then we have e to the x plus 1. Then we have e to the x plus 1 over x squared minus 1 over x. All that divided by, flip the bottom. But I'd need a common denominator up on top, which would be x squared. E to the x, x squared. Plus 1 minus x. Okay, and times that. We have x squared here. And e to the x here. If I multiplied everything by e to the power x, then this would be e to the power x squared. And that's not what I want. I want x squared by itself. E to the power. So I had originally x to the power of that, g me put it this way. So e to the x over negative e to the x over x squared minus e to the x over x over e to the x squared. That times that is that. Minus this times 1 over, this is 1 over x. That makes it even smaller. But it should work. Well, I'll work on it this weekend, but it should work. But anyway, that is the answer. It should gotten,
Definitely.
yeah. Because what I was thinking about doing is just distributing. So you have x squared over x plus e to the x over x, and just doing. So this one you have x plus ex over x. So this one's pretty done. And you just do the quotient there, which is what this one should have done.
I tried to use the quadro because it might be easier than the quotient rule,
Mm-hmm.
because I thought.
Well, yeah. Which is what I was thinking at first.
But it's possible.
That was not the fast.
No.
Yeah.
How about this one? What's the derivative of this one? We've done pretty quick.
2 times.
2x times e times.
2e to 2x.
Yeah.
About this one? Well, how about, what's this one going to be? So now we have this equation. Actually, well, okay, this one here is thinking about simplification first.
Oh.
The top is the difference of two squares. So it's t plus 1, t minus 1. The bottom one is a sum of two cubes, which is t plus 1, t squared minus t times 1 plus 1. So t plus 1's cancel. So our function really is this. As you guessed, we have to combine product and quotient rule at the same time now. You guys want to try it on your own first, or? Yeah, try it on your own first. What's different about the bottom number here as opposed to the other ones we've done? This is a monomial. Whenever you have monomial and a function, it's much easier if we simplify it. So let's look at our function. X minus one. Can we do anything with the second one?
Or well, you can factor out X.
You can factor out an X. Why is that going to be good? Is because we can cancel one of these now. Now it's much easier if we multiply the top, we get x squared, -2, -1, so -3x plus 2 over x cubed. Now, since it's a monomial on the bottom, we can take each of these separately. Because now we have much smaller equations to deal with. So those are gone. So we have 1 over x. We have 3 over x squared. Now we just take the derivative of each one of these separately. We know the derivative of this first one. It's x to the power -1, which makes it -1 x -2, makes it -1 over x squared. We've done that a couple times already. So this first one is -1 over x squared. Three times x to the power -2. Now bring that, so it's -6. Six over x cubed. Remember, I told you the denominator just changes by 1. Yeah, which would be -6 x to the -4.
Then do we need to combine?
Well, yeah, if we have two negatives here, so that becomes a positive. Yes, and then we'd have to get a common denominator. Which, and these are opposite signs, so it's minus. What's the LCD? Yeah, so this one's just missing 2 more x's. This is just 1 x. So -x squared plus 6x minus 6 over x to the 4th. Well, remember, we start off with x to the 3rd, so we know our denominator has to be x to the 4th. So whenever you have a monomial for the denominator, split them up. Simplify the top, do everything you can. And that's what I noticed when I noticed this right here. I said, hey, if we can cancel, that makes it a little easier. So it's much easier if we go to these small equations. Yeah, it looked, I know what you guys are doing. You're doing, this is the f of x, this is the g of x, and you're doing the product rule. I started took a step back and thought about it, but it's monomial. Rule of thumb, monomials are friends on the bottom. Now, here's you asked me a week back, can we take more than one derivative? Yes. Take the first 4 derivatives of this function. Mhm. The fourth. And you repeat the same process. So polynomials are easy, but if we had a quotient, it would be painful. It'd be because it would keep on growing.
Yeah.
So yeah, and that's it. Those are the shortcuts. Now we are going to speed up because now we don't have to worry about just the trivial. But we know where this stuff came from. We know when I said derivative, we know the function has to be continuous, has to be differentiable everywhere in that domain. That means the limit has to exist. That means it has to exist in both directions. And if it's a closed interval, closed bound, it has to be one-sided at the end. So we know all this stuff. Now we speed up and just worry about what this is all about. Yeah. We're getting to a point where we're talking about related rates. That's another fun thing of this is you start off with a function and how does one part relate to another part? Like, for example, if you toss a pebble in a lake that makes circles, and you can determine how big it's going to be after how many seconds by seeing how fast they're growing. Ripples, yeah, and all sorts of stuff. So then now we can go into trigonometric functions too. All right, guys. So have a great weekend. Do your homework. Oh, and don't worry so much about